Look around our laboratory. We will be using all kinds of equipment this year as we learn chemistry together. We will use simple pieces of equipment, such as the meter stick, all the way to more advanced pieces of equipment, such as the digital balance. As we study chemistry together, we will need to know how to use our equipment correctly. After all, chemistry depends on accurate and precise measurements.
It's true that modern chemistry depends on accurate and precise measurements. Let's see what you already know. Do you know how many ounces are in a cup? Or do ounces make up pounds? How about the number of feet in a yard? Or in a mile? Do you know how many teaspoons are in a tablespoon? It's hard to keep track of all these facts. So hard, in fact, that most of the world refuses to do so. Instead, they use the metric system. In the United States, we primarily use the English system of measurements. This system is very old and has evolved over the years. For example, the measurement of a foot is now equal to 12 inches. But originally, this measurement was based on the size of the king's foot. Of course, this standard of measurement would change every time the king changed. Some modern examples of the English system of measurements include the cup, the ounce, the inch, and, for those trying to lose weight, the dreaded pound. However, the metric system has crept into our lives over the years. Some examples include 2-liter soft drinks and 35mm film. Since most other countries use the metric system as their measuring system, it would seem to make sense for the United States to change over. Of course, that would be a very costly endeavor, not to mention the public outrage over such a thing. So, for now, we grow up knowing the English system, and it becomes necessary for us to learn the metric system in our science classes.
During this lesson, you will define length, mass, volume, time, and temperature. Name the SI unit for each and an instrument used to measure each. And make measurements using the correct unit, as well as the correct number of significant digits.
In chemistry, as in all sciences, we will use a measuring system called the International System, which is abbreviated SI. It seems backwards, doesn't it? You know that we try to confuse you as much as possible in science classes. No, just kidding. The SI abbreviation comes from the French. Of course, the common name is just the metric system. We are going to discuss 5 types of measurements that are commonly used in chemistry.
Length is defined as the distance between 2 points. The base unit for length is the meter, which is abbreviated with a lowercase m. In class, length will be measured using a metric ruler or a meter stick. An example of a length measurement would be the distance a car or truck travels. Unlike the U.S., in most other countries, highway signs express distance in kilometers. Mass is defined as the amount of matter in a substance. The base unit for mass is the gram, which is abbreviated with a lowercase g. In class, mass will be measured using a balance. An example of a mass measurement would be that a typical paperclip has a mass of about 1 gram. Volume is defined as the amount of space an object occupies. The base unit for volume is the liter, abbreviated with an uppercase L. In class, volume will be measured using a metric ruler when measuring the volume of a solid, and a graduated cylinder when measuring the volume of a liquid. Think of a 2-liter soft drink bottle. It does not matter if the bottle is filled with sand, soda, or air. The volume still remains 2 liters. Time is defined as the interval between two occurrences. The base unit for time is the second, which is abbreviated with a lowercase s. In class, time will be measured using a stopwatch. A good example of measuring time is how students watch the clock to see when class is going to end. Temperature is defined as the measure of the average kinetic energy of a substance. The base unit for temperature is Celsius temperature, abbreviated with a degree sign and an uppercase C, or Kelvin temperature, abbreviated with an uppercase K. In class, temperature will be measured using a thermometer. When you want to stay home from school, you might take your temperature and hope for a fever. Of course, now that you're in this exciting chemistry class, you can't wait to get to school each day.
Now, let's play Junior Chemist again and do some measuring. We will start by doing some length measurements. Your local teacher will give you a ruler to work with. The first thing you need to do is check to be sure that your ruler is a metric ruler. Take a close look at your ruler. If it only measures inches, throw it away. Okay, that may be kind of drastic, but it will be useless to you in science class. You need to make sure your ruler also measures centimeters. Now, take a minute to measure the width of your textbook. Be sure to measure in centimeters. Write your answer in your notes. Local teachers, please pause tape now. Now, let's put some possible textbook measures up on the board and see how we did. 20 1/2. 21. 8. 20.6. 20.63. 20.64. 8.2. Well, I think that's enough to illustrate some very important points. First of all, none of the answers written on the board are true measurements. They are all just numbers. A measurement includes both a number and a unit. I think you had better write that in your notes. I'll say it again. A measurement includes both a number and a unit. All of the answers written on the board are missing the unit. Because we are all making the same measurement, we know that the unit here is centimeters. But someone walking in off the street wouldn't know if we meant 20 brownies or 20 pieces of paper. Now that we have that cleared up, let's look at each of our measurements and try to figure out which is the best measurement for the width of our chemistry book. The first measurement is 20 1/2. First of all, in chemistry, we make it a practice to write decimal numbers instead of fractions. That would make this measurement 20.5. I mean, 20.5 centimeters, of course. This is a reasonable measurement for the width of our book. Let's put it aside for now as we look at some of the other measurements. The next measurement is 21. This seems very similar to 20 1/2. If you look down the list, there are 3 other measurements that are in the same ballpark. Then, there are 2 that seem totally out in left field. The students who measured 8 and 8.2 forgot that this is a science class and measured in inches. We can throw these 2 numbers out. So, how do we determine which of the remaining numbers is the most correct? To determine this, we need to talk about significant figures. Doesn't that sound important? Okay, first things first. Students always want to know why we even bother with significant figures. Sit back and relax while you hear a little story.
Once upon a time, a student was given the task of having a metal cube made for a project at school. She was told that the cube needed to have a volume of 10 cubic centimeters. Being the intelligent student that she was, she knew that taking the cube root of 10 would tell her how long the cube's edge needed to be. She found that each edge needed to be 2.154 centimeters long. She knew that her friend had done a project similar to this last year, and she asked her friend where she went to have the cube made. She took her plans to the metalworker shop and asked if they could make the cube. The metalworker said, "Yes, we can make this according to your specifications, but it will be expensive." The student told the metalworker to go ahead with the project. Her friend had told her that it cost her $35 the previous year, and she had been given a budget of $50. She returned to the metalworker shop the next day, expecting the job to be done. "Sorry," said the metalworker, "we're still working on it. Try next week." Finally, the day came. The student got her cube. It looked very, very smooth, shiny, and beautiful in its velvet-lined case. Seeing it, she feared disaster and became a bit nervous. When she asked for the bill, the metalworker said, "It comes to $500. "How can that be?" the student asked. "My friend had a similar one made last year, and you only charged her $35. "My dear," the metalworker replied, "your friend asked for a cube that was 2.1 centimeters on a side. That was easy. But you asked for 2.154. It took us several tries. The first one we made came out 2.151 on each side. The second one was closer, but still not what you asked for. On the third try, we finally got it right." "Oh," said the student, who learned a valuable lesson in significant figures that day. Significant figures are numbers in a measurement that are certain, plus one estimated number. For example, suppose we are going to measure the length of this nail. The nail clearly measures between 6 and 7 centimeters. In fact, it clearly measures between 6.3 and 6.4 centimeters. Following the rules for significant figures, the length of this nail would be 6.3 something. Let me explain. The 6 and the 3 are certain, so they must be included in the measurement. The something represents the estimated number that must also be included. Because it is an estimated number, it may not be exactly the same for every person who makes the measurement. One person might measure the length of this nail to be 6.35 centimeters. The next person might measure it to be 6.36 centimeters. Both answers are equally correct.
Let's apply this information to our measurements of the width of our textbook. If you look again at your ruler, you will see that it has markings for each tenth of a centimeter. That means our measurement should go one digit beyond the tenths place to include our estimated digit. However, our measurement should include the hundredths place. This means that two of our answers are acceptable, 20.63 and 20.64. Which is correct, you say? Both are. Remember that the estimated digit is just that, estimated. Everyone will not make the exact same estimate, and that's okay. Now, we are going to make some volume measurements. We are going to want to make sure we read our instruments correctly as we make these measurements. First, let's find the volume of a liquid. Here, we have a graduated cylinder with a colored liquid in it. In your notes, write down the measurement you read. In case you have forgotten, a graduated cylinder like this one measures in milliliters. Now that you have made your measurements, let's see how you did. Let's put some of your possible measurements up on the board. 26 milliliters, 25 milliliters, 25.5 milliliters, 25.4 milliliters, 25.5, 26. Okay, let's see how we did. First of all, does anyone see any numbers that are not true measurements?
The 25, the 25.5, and the 26 are all missing the unit of milliliters?
That's correct. Always include the unit in a measurement. That leaves us with 4 other choices. Can anyone tell us which of these choices are correct and explain why?
The graduated cylinder has a marking for 25 milliliters and a marking for 26 milliliters. Our volume is somewhere between these two amounts. Using significant digits, we would say 25 point something, with the something being the estimated digit. So, I would say that both 25.5 milliliters and 25.4 milliliters are correct.
Excellent. Now, let's talk about measuring the volume of a solid. We are going to refer to solids in two ways. Solids, for which we know a formula for calculating the volume, are going to be called regular solids. All other solids will be referred to as irregular solids. First, we are going to find the volume of two regular solids. Take a look at this cube. Its sides have a measurement of 3.0 centimeters. You should remember from math class that the volume of a rectangular solid is equal to its length times width times height. Are you writing this down? The volume of a rectangular solid is equal to its length times its width times its height. Apply that principle to this cube and see if you can calculate the volume. Jot your answer down in your notes. You should have multiplied 3.0 centimeters times 3.0 centimeters times 3.0 centimeters to come up with 27.0 with some unit. Some of you probably put centimeters, but you need to put on your math hat and think again. You are multiplying centimeters times centimeters times centimeters, which gives you centimeters cubed. You will find that if you write the units all throughout the problem, it will be much easier to keep track of them. Now that we've got the hang of this, let's try another one. You have a rectangular solid with a length of 5.0 centimeters, a width of 3.0 centimeters, and a height of 1.0 centimeters. What is the volume of this solid? Well, you should have multiplied 5.0 centimeters times 3.0 centimeters times 1.0 centimeters to get 15.0 centimeters cubed. That's enough of those, but what if we want to find the volume of an irregular object? Perhaps a rock. Any ideas? How would we measure the length, width, and height of a rock? Does a rock even have a length, width, and height? Your local teacher is going to pause the tape for a minute and let you try to come up with some ideas. Did you come up with some good ideas? Did anyone suggest trying to find the volume by a method called water displacement? You probably learned about this in middle school, but just in case you have forgotten, let's go through the process. The first step is to pour some liquid, usually water, thus the name, into a graduated cylinder and record its volume. Students always ask how much water they should put in. It doesn't matter. Let's finish going through the process, and then we will discuss why the amount of water doesn't matter. Let's record the volume of water in the graduated cylinder. Don't forget about significant figures. Since our graduated cylinder measures to the ones place, you will want to record your volume one digit beyond that to the tenths place. So, we have about 45.2 milliliters of water in our graduated cylinder. Now, we carefully put the irregular object, the rock in this case, into the water and measure the new volume. If you look at the graduated cylinder, you see that the new volume is 47.5 milliliters. So, how do we find the volume of the rock? Well, the amount of water in the graduated cylinder has not changed, so we can subtract the two measurements to find the volume of the rock. This would make our rock's volume 2.3 milliliters. This is called water displacement because the volume of the object is equal to the amount of water it displaces. You'd better write that down. To find the volume of an irregular solid, you will use water displacement. The last measurement we want to practice making today is the mass measurement. There are many different kinds of balances. You have probably used a triple beam balance in a middle school science class. There's a good chance that you will be using a triple beam balance when you do labs in your schools. Another type of balance is a digital balance, which is easier to use. We will be using a digital balance for the labs performed on the video programs. The digital balance we will be using in our labs measures to the hundredths place. Let's learn how to use it. Let's find the mass of this rubber stopper. First, we want to turn the balance on. Then we push the tare button and wait for the balance to read 0.00 grams. Next, we put the stopper on the balance and we have our mass of 13.35 grams. Well, that seems pretty simple. Now, let's find the mass of this cup of water. We'll just push the tare button again to get the balance back to reading 0, and then we pour the water on the balance.
No!
What? Oh, you're right. We can't pour the water directly on the balance because it would spill all over the place. So, we're just going to measure it in the cup and assume it's close enough.
No!
So, you don't think that's a good idea either? What if we take this other cup and measure its mass first? The mass is 15.42 grams. Then we could pour my water into that cup and mass it again. The new mass is 35.44 grams. By subtracting 15.42 grams from 35.44 grams, we would have found the mass of the water. The mass of the water would be 20.02 grams.
Yes!
I agree that this is an excellent way to find the mass of water in this cup. However, our digital balance makes it even easier for us. We can put the empty cup on the balance and then push the tare button. Again, our balance reads 0.00 grams, but this time it is including the cup. Now, we can just pour our water in and read the mass. Let's be honest. It isn't that much easier than just subtracting, but there is another application of this that will definitely come in handy. Let's suppose we need to measure 2 grams of salt. We can place an empty cup on the balance and push the tare button. Then, we keep pouring salt into the cup until the balance reads 2.00 grams. Thanks to the digital balance, massing is fairly simple. We have introduced several measuring skills and techniques, so let's take a few minutes to let you practice what you have just learned.
In your notes, show all of your work as you find the volume of the rock. Of course, the way to solve this problem is to use water displacement. The volume of water in the graduated cylinder before the rock is added is 25.0 milliliters. After the rock is dropped in, the volume is 28.5 milliliters. So you subtract 25.0 from 28.5 to get 3.5 milliliters as the volume of the rock. Okay, now find the volume of this rectangular solid. It has a length of 4.0 centimeters, width of 2.0 centimeters, and height of 1.0 centimeters. To find the volume of this solid, you multiply 4.0 centimeters times 2.0 centimeters times 1.0 centimeters to get 8.0 centimeters cubed. Now suppose you drop this same solid into a graduated cylinder that has 30.0 milliliters of water in it. The water in the graduated cylinder rises to 38.0 milliliters. What is the volume of the object? Well, 38.0 milliliters minus 30.0 milliliters gives us a volume of 8.0 milliliters. So we calculated the volume of the rectangular solid 2 different ways. One way, we got 8.0 centimeters cubed. Another way, we got 8.0 milliliters. What does that tell us about a centimeter cubed and a milliliter? Exactly right. 1 centimeter cubed is equal to 1 milliliter. You must remember this or it will trip you up. 1 centimeter cubed is equal to 1 milliliter.
I believe we've done enough measuring for one day. You must be sure to study your notes before our next lesson. You need to make sure that you are familiar with the metric system. It is important to remember that chemistry is a course that builds, so you must not let yourself get behind in your studying. Stay on top of it and you will be able to enjoy this adventure. Now, it's time for you to show what you know. Since we have moved beyond our first lesson, you will see that there is a new aspect of the chemistry quiz. Each chemistry quiz will feature 2 questions that are a cumulative review over anything we have learned. Following the 2 cumulative review questions will be the questions over today's lesson. Remember that you do not need to write down the questions, just the letter of your answer. When the tape ends, your local teacher will go over the correct answers with you. Here goes.
Here's cumulative review question number 1. Which of these is a quantitative observation? A. The candle is 3.0 centimeters long. B. The wick of the burning candle is curled at the top. C. The wax contains carbon and hydrogen.
Cumulative review question number 2 sums it all up. Chemistry is the study of A. Candles, B. The metric system, C. Reactions, D. Matter.
Okay, question number 1 from today's lesson. The instrument used to measure mass is the A. Graduated cylinder, B. Ruler, C. Balance, D. Stopwatch.
You will need your math hat for question number 2. What is the volume of a cube if each side measures 2.0 centimeters? A. 8.0 centimeters. B. 8.0 centimeters cubed. C. 2.0 centimeters. D. 6.0 centimeters cubed.
Number 3 is, a graduated cylinder has 20.0 cubic centimeters of water in it when a marble is dropped in. The water level rises to 21.5 cubic centimeters. What's the volume of the marble? A. 20 cubic centimeters. B. 21.5 cubic centimeters. C. 1.5 cubic centimeters. D. 41.5 cubic centimeters.
Last but certainly not least is question number 4. The process used to find the volume in question number 3 is called A. Water displacement, B. Water subtracting, C. Irregular volume,
Well, it's time to go. Happy measuring until we meet again.